Thank you, Nina, for the kind introduction. And also, I would like to thank the organizers for inviting me, especially Maria. But I think, yeah, I don't see her, but I met her in last year in GEMS conference, and it was quite nice meeting her. So it is not really a scientific talk because I promised I will give a tutorial. So I will try my best. So as an outline, I will start introducing my group, and then I will introduce the two main techniques that I'm working on, molecular beam epitaxy and pulse laser deposition. Then I will introduce a hybrid pulse laser deposition technique, which we are currently developing and almost done developing. And then I will give a brief outline about the magnetic properties of chromium tellurides and why we are going to investigate this material. So I highlighted red for the results part. I will not show the results here, but I will also show two other projects like a teaser that we are currently working on. Okay, so this is my profile. I did my PhD at a CSIR institute in India, and then I spent a few more months there for postdoc, but I also went to University of Nova Gorica for my, during my PhD time for doing some experiments. Then I went to Darmstadt for my first postdoc, and then I continued there as a principal investigator on a DFG project, and then since last year, September, I am in Goettingen. So I hired my first PhD student recently, and I have a few other students and research assistants working on complex thin film systems or advanced epitaxy, and we are also constructing a new personal group website, advancedepitaxy.com. But if you are interested, you can already see some news in the university's website. Okay, so this is exactly what we are doing. So I have a feeling that most of the people working here are doing advanced characterization. So you will be here, or you will be this person writing the paper, or this person thinking about the results. Because yesterday one of the speakers mentioned something that they always think what the hell is going on with the data. But we would like to modify that thought. Please always think what the hell is going on with this material. Because sometimes it's not really the result that is giving you this complicated thought and making an injury in your brain. It should be sometimes, or it can be sometimes, some defects inside the material. Maybe you are not getting the perfect material, but you are investigating this material assuming that you got the perfect material. So this is the usual flow. From the synthesis lab, the material goes to the advanced characterization. But we would like to go back to the synthesis lab after the characterization, and we need information about the defects in that material. What kind of defects is contributing to the properties? Because this guy, or so guy is a gender neutral term, I would say. So this guy can modify the material properties according to the defects. Because as a material science engineer, this person will be able to modify the crystal structure or electronic structure, or can also introduce additional effects like interface effect or surface effect. So we are mainly doing functional properties with respect to magnetism, optoelectronics, photovoltaics, and electrocatalytic application. And material systems, we are currently working on metals, oxides, oxynitrides, and recently we started chalcogenides. And we are doing mainly by using UHV-based technique, pulse laser deposition, and molecular beam epitaxy, but we are also working with the metal organic aerosol deposition, which is a non-UHV-based technique. But here I will introduce only these two techniques. So here this picture I always liked to show in all my presentations, because this is the one of the greatest labs for thin film growers in the world, because here you see this is the pulse laser deposition system where you can grow materials, and after the deposition you can in situ transfer it into the oxide MBE chamber. Not many people have oxide MBE chamber. A lot of people are working with the nitride MBE, but in our lab we had this nice system where you can transfer the material in situ and back and forth between these two techniques. And also I would like to show you one thing, that all the people working in that lab were girls. Most of the time we were a female oriented or female dominated lab, and I think that's not common in Germany, but this was like this in Darmstadt. I don't know why. So I would like to briefly give the classification of deposition methods. Probably you have taken your car to a workshop and got spray painting on the car. So that's also one of the deposition techniques that you can use. But most of the material scientists work with the physical vapor deposition or chemical vapor deposition. So this comes in the gaseous category. So this classification is according to the state of the material that is being transferred from the source to the substrate. And in the case of PVD and CVD, the state is gas. And the further classification between PVD and CVD is based upon the state of the material that we are using as a source. In the case of a chemical vapor deposition, we use gas, and in the case of a physical vapor deposition, we use solid material. And one important point is that we do not expect any chemical reaction during the transport or at the surface of the substrate when we are considering a physical vapor deposition. If there is a chemical reaction during the transport, then it's not a PVD, it's a CVD technique. And if you want to modify the material's property by changing fine structure or electronic structure, it's better that you use a physical vapor deposition. And pulse laser deposition and molecular beam epitaxy comes under physical vapor deposition technique. So here is the schematic of a molecular beam epitaxy. Here you can also see an oxygen inlet. This is what makes the system an oxide MBE. Oxide MBE is also known as a reactive MBE because not all the UHV parts are compatible with the reactive gases. So you need special UHV parts if you want to grow oxides in an MBE. So in a molecular beam epitaxy, the first step is to generate the fluxes of individual elements, and that's what we call molecular beam. And then the nucleation and the film growth happens at the surface of the substrate afterwards. We can have different sources of molecular beams, like Knudsen cell based effusion cells, or you can also use electron beam evaporation, and you can attach several sources of molecular beam in a MBE system, and you can get the deposition at the surface of the substrate. But we are usually choosing the source depending upon the element that you want to grow. Not all elements can be evaporated by using electron beam, but in that case you have to go for an effusion cell. So here this is the Knudsen effusion cell. It is just like a thermal evaporation, but you need to have a closed cell. You keep the material inside this closed cell and you heat the cell by using heater wires, and the material will be either sublimated or evaporated, but inside the cell, and after some time there will be a vapor and solid liquid phase equilibrium achieved. In that case, the pressure, the partial pressure inside the cell will be constant, and you can control the flux rate of the material coming out of this exit aperture by varying the temperature of this cell. So this is how a Knudsen cell works, and if you want to evaporate highly volatile material, you have to use such a device, otherwise you will destroy the entire chamber. And this is how we use electron beam evaporation pocket. So in my former group, we had 6 electron beam pockets. We can simultaneously evaporate them. And we take the elemental sources in its solid form like this. So depending upon the material, you have to take them in different ways. So this was strontium, this is niobium. So niobium is a refractory element, and if you want to use niobium in an MBE, you cannot use just an effusion cell. You always have to go for a electron beam evaporation. So in this case, you are heating a filament, and due to thermionic emission, electronic emission, you get a lot of electrons here, and these electrons will be deflected and directed to the source by using deflecting magnets, and this will evaporate this material, and finally you get the vapor of this material. And the energy in this case, in the case of a fusion cell, you were controlling the rate of evaporation by using temperature, but in this case you are controlling it by using the energy of the electron beam. So usually people ask, what can you synthesize by using an MBE? Or some people, if you are not a believer, you can also say that what can you create by using an MBE? Because in this case we are creating certain materials that is not thermodynamically stable otherwise in nature. So in principle, we usually say that we can grow anything if that element is stable. So we just have to choose the right source of the molecular beam and just start the deposition. But there is one problem. If I want to grow a material with many elements, then I have to optimize each of the element and how it is behaving inside the chamber, and also the behavior of one element will be different in presence of the other one. So this will take quite a lot of time. That's why MBE is not really good for growing a brand new material which has many elements. So this is one example of the steps that I took until I finished optimizing the growth of an oxide material SRNB03. So each step took at least 3 months for final optimization. So this is the main problem, and in such cases, if you are directly growing such a material, it's easy and it's convenient to use a pulse laser deposition. In this case, the advantage is that you can use the target of the desired composition. So if you want to grow SRNB03, you don't have to provide strontium here and niobium here and the gas surrounding, as in the case of an MBE. But in this case, you can use a stoichiometric SRNB03 target and you can directly start the deposition. But there is a problem in the case of PLD. It creates preferential ablation of the material, and sometimes the stoichiometry will not be transferred into the substrate. This is the case if you are using chalcogens CRTE or CR2TE3. If you use a CR2TE3 target here, most of the time you will not get CR2TE3 in the film. So this is a problem when you have materials with a different volatility. And in such cases, you have to use MBE, but as I said, MBE also has many disadvantages when you grow materials containing many cations. And that's the main reason why we are developing the hybrid pulse laser deposition technique. In this case, you can directly deposit the material. Just like in the case of electron beam evaporation, you can use the PLD target for getting cations like chromium or strontium or niobium. But if you want to use highly volatile element like tellurium, you cannot give the tellurium from PLD target. In that case, you have to supply it in the form of a molecular beam source. And that's what we are currently developing. And in addition to this, we also have a radio frequency plasma source for gases in our hybrid PLD system, because this type of plasma source is usually attached to an MBE where you need to grow nitrides. In the case of a PLD, you can already supply the nitrogen inside the PLD target. But if you want to grow oxynitride or nitrogen and tellurium mixture, you have to go for such a technique. And we already implemented the plasma source, and this is being attached, and currently we are growing chromium tellurides in this chamber. So we have 3 PLD chambers, and we are growing different materials in different chambers to avoid cross-contamination. And here I highlighted the characterization, these 2 characterization, because when you go for advanced characterization on a material that you received from another group, you always have to verify if they did all this structural characterization at least, because sometimes, so yesterday many people were mentioning about the oxides and oxygen and selenium containing material. But in most of the talk, if I ask them what is the oxidation state of the cation, not many people would know the oxidation state, because they don't care about it. If the thin film grower gives them the sample saying that, okay, this is the material, they start investigating on this material by assuming that it is in the perfect stoichiometry and perfect electronic state. But this is also important if you are storing the material in a glove box for a few years. Sometimes you get the best material from the thin film growers and you get really good results, and you keep it in the glove box and investigate it after a few years. But in such cases also the structure or the electronic state could be different after a few years. So always go for such structural characterization before doing advanced characterization. So here we are growing chromium tellurides. We selected chromium telluride as the first material because it's also magnetic. And in this case, we are providing the chromium from the PLD target and tellurium from the molecular beam source. And our long-term plan is to grow chalcogenide and 3D perovskite oxide interfacing, because if you want to grow a 3D perovskite oxide, the best technique is to use a PLD, and if you want to grow a telluride, you need a molecular beam source. So we believe that we could easily combine these 2 versatile material system in our experimental setup. And the question why chromium telluride, as I said, it is magnetic, but depending upon this X and Y, they are showing different crystal structures. So it's quite a lot of possible structures. There can be 1:2, 5:8, 2:3, 3:4:1:1. All these structures are possible, and all these structures are showing ferromagnetism. Some are showing ferromagnetism at room temperature and a huge perpendicular magnetic anisotropy. So these 2 physical properties at room temperature can be easily combined for spintronic devices together with the other 2D material. But in that case, it's important to know if the origin of magnetism is really the lattice of this material, because depending upon the deposition technique or deposition conditions, or even depending upon the group who is growing this material, they are getting different magnetic properties, and that's not nice. And that's why we would like to investigate on this material, carefully controlling the defects in this material, and also by adjusting the ratio between chromium and tellurium. So people started to grow this material by using pulse laser deposition, by using target of CR2T3, and they ended up in chromium telluride CrTe thin films, but they also found quite a lot of other phases of chromium and tellurium in their film. So as I said already, it's difficult to grow such materials by using a PLD, and people also reported chromium telluride thin film by using molecular beam epitaxy. So it's obvious that depending upon the deposition conditions or substrate or whatever the material is showing different magnetic behavior, but the interesting point is that here you can see the material has a TC around 165 Kelvin, but somehow they also said that this material has a TC above 400 Kelvin. So in my case, I would not believe that this will be a magnetic phase. Here it could be a ferromagnetic short range correlation or something. But they measured the out of plane MH hysteresis loop and found convincing MH curve. And they suggested that this material is a high temperature ferromagnet. And in this work also you can see the magnetic moment is not completely zero. And in another report, they even observed the TC about the room temperature, but in this case, when they measured the magnetic moment in plane in two different directions, they got different hysteresis loop. So this is a problem when you grow thin film. If you are getting magnetic properties or any physical properties inhomogeneously, then first of all you have to check if the structure is homogeneous or not. If you are growing a homogeneous thin film and you are getting anisotropy in plane, then this means that either it's really originating from the structure or the film was grown with a gradient, either in stoichiometry or in the crystal structure. And in this case, so this was CrTe, and I also checked for other films. This is the same for CrTe2 films. So here in this case, they were able to grow the CrTe2 film successfully by using PLD and found the TC. But when they grew it with molecular beam epitaxy, they found that this material again has a magnetic moment at room temperature. And here this is the XMCD result for the chromium spins. And here you see this small increase, and they said they suggested that this could be the starting of another magnetic phase. And there are quite a lot of reports coming recently on this material, as you can expect, because room temperature magnetism is highly important, and if this is a 2D material, then you can use it for a lot of application. But here you see in these three reports reported the magnetic moment in EMU. They are not even reporting, so here I didn't include that MH curve or MT curve, but these reports are reporting the magnetic moment in EMU unit, or they are not reporting it in absolute unit. So that's the main point why we have to be doubtful the origin of the magnetic moment, if it is really the lattice of the chalcogenide or not. And in this case, you can see even a few monolayers of CrTe2 is showing almost near room temperature magnetism, and the TC is increasing when the thickness is increased, and that's the same case with the Cr2Te3. The TC is increasing when the thickness is increased. And in these two cases, they were epitaxially stabilized by using molecular beam epitaxy, and most of the 2D people are working with the van der Waals epitaxy. In that case, they take the big solid material and they use a scotch tape to get the layers out of the material. And when they tried it with the van der Waals epitaxy, the TC, the trend in the TC is opposite to what they observed for the case of epitaxial film. So overall, if you say that a material is magnetic, you should see if the magnetism is really originating from the lattice or if it is some extrinsic effect. And here I would like to stress again, so when you investigate magnetism on a material, it's extremely important if the oxidation state of the cation is what you are expecting from the lattice, and if the stoichiometry is correct, and if you have any interface effect. Otherwise, there could be a lot of reasons why the magnetism is originating, especially since most of the dirt that we have in the air or flying around are magnetic. They contain iron or iron oxide, and they are magnetic. And even when we take the thin film by using a metallic tweezer, sometimes we get magnetism just because we used the metallic tweezer. And when you look through your characterization techniques, probably you are seeing the spin coming from this dirt. So yeah, because of that, from our side, we want to elucidate the problem or the defects associated during the growth itself, and we want to provide the best samples for you people. And here, interestingly, I would also like to show this graph. Such interfaces, oxide, nitride interfaces, are also showing a room temperature ferromagnetism. This is chromium oxide and chromium nitride interface. And this is just because of the electronegativity of the two phases. There will be a charge transfer between these two cations, and they provide the sufficient exchange interaction, and they are showing the magnetism. So this can also be the case for chromium telluride material, and we are not yet sure the origin of the magnetism in this material, and that's what we are focusing on, a series of samples with the controlled defects, because defects are also important sometimes. The point is that we have to control it. So that's the talk about this chromium telluride, and as a final say, I would also like to advertise two projects that we are currently working on. Since you have seen that we also have the radio frequency plasma source attached to the PLD, we are capable of growing oxynitrides, and here we are investigating on the magnetic properties of certain materials with their oxygen evolution and oxygen reduction reactions. And in another project, we are working on gradient bandgap engineering in transparent conducting oxides towards photovoltaic application. And here I would like to thank my contributors for this presentation. So this is my group developing this hybrid PLD technique at the moment, and these are the funding agencies who funded my research since my PhD until now. And I would also like to thank two of my former supervisors, Professor Warma from CSER lab and Professor Lambert Al from TU Darmstadt. So with this, I would like to thank you all. And since this was a tutorial, you could ask any questions, and maybe I would also like to ask you some questions if there is time. Okay.